Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to talk on the module Optoelectronic Devices from the paper Measurements and Instrumentation. In this module, the students will be able to understand about the optoelectronic devices, which are also known as the photoelectric transducers. Here we will study about the photoemissive cells, which are of three types: vacuum type photocell, gas filled photocell, and photomultiplier tubes. We will study about the photovoltaic cells, then the photojunctions, which are of two types: photodiode and phototransistors. Optoelectronic devices or photoelectric devices are light operative devices. They might be light emitting device or devices that modify light. They are categorized as photoemissive, photoconductive, or photovoltaic. In photoemissive devices, as radiation falls over a cathode, electrons are emitted from its surface, whereas in photoconductive devices, resistance of the material changes when their surface gets illuminated. In most photovoltaic cells, output voltage is proportional to radiation intensity. Any light source emits energy over a certain range of frequencies or wavelengths. The curve of either frequency or wavelength against the energy output is called emission spectra of the source. Generally, electronic devices are sensitive to certain range of radiation frequencies. When a curve is drawn between the device current, resistance or voltage and radiation frequency, it is known as spectral response. A threshold frequency is the minimum frequency that can create a photoelectric effect. Photoemissive cells or tubes. There are two types of photoemissive tubes. They are basically vacuum type and gas-filled type. Photomultiplier tubes also fall in the category of phototubes. Vacuum type photocells or phototube. These devices have a thin metal curved sheet with a concave surface coating with photoemissive material, forming a cathode, and a rod mounted at the center of the cathode plate is anode. This whole setup is enclosed in a vacuated glass tube. The most commonly used photocells have cesium antimony surface and is known to have high sensitivity in the visible spectrum. Type of glass used in the tube determines the sensitivity of the device to other wavelength. The assembly of the phototube is shown in figure 1. The glass normally cuts off the transmitted radiations in the UV region. When incident radiant energy falls on the cathode plate, electrons emitted are emitted from its surface and are collected by the plate or anode. The current through the photocell depends on, first, the intensity of light, second, the wavelength of the light, third, the voltage applied across the cathode and the plate. Photocurrent response of the vacuum phototubes is linear over a wide range, so much so that they are often used as standard in light comparison measurements. This linear relationship is shown in the figure. The main advantage of a photocell is its stability, and their characteristics don't change much over long periods of time, provided they are operated at low voltages and protected against excessive current. The main drawback of such device is its low sensitivity. These tubes are best for observing light pulses of short durations and when light is modulated at high frequency. Now, let us consider the gas-filled photocells. These photocells were designed to overcome low sensitivity of vacuum-type photocell. The sensitivity of the device is improved by increasing the number of electrons produced at the cathode by a gas discharge. There is not much in the construction of vacuum tube and a gas-filled photocell, except that the latter one contains an inert gas, usually argon, at low of 1 mm of mercury. When electrons are emitted through photoelectric cathode and if their energy exceeds the ionization potential of the gas, collision with gas molecules result in the formation of positively charged ionized gas molecule. This also creates a secondary electron along with a positive ion. By increase in the voltage beyond ionization potential, the anode current further increases due to the higher number of collision between the photoelectrons and gas molecules. The gain over the response as compared to vacuum tube is between 5 to 10. A resistor is always connected in series with a gas-filled tube. This limits the anode current and prevents an accidental overvoltage. The luminous sensitivity of gas phototubes is between 40 to 150 microampere per microvolt. Few drawbacks of photo-filled gas tubes are: first, they are comparatively less stable when compared to vacuum tubes. Second, they show non-linear characteristics. And third, they have time-lagged response to modulated or chopped light frequencies above 10 kHz. Motion picture industry uses gas-filled phototubes as sound-on film sensors. Students, now let us consider the photomultiplier tube. Photomultiplier tubes are extremely sensitive to detect very low level of luminous intensity. A multiplier tube is made up of an evacuated glass envelope with photocathode, an anode, and several electrodes known as diodes. Its principle of operation is illustrated in figure 3. In the tube, electrons emitted by photocathode are electrostatically directed toward a secondary emitting surface known as diode. On application of appropriate operating voltage to diodes, 3 to 6 secondary electrons get emitted for every primary electron strike at diode. These secondary electrons are directed towards a second diode and the process gets repeated. This multiplies original emission from photocathode from current of the order of few microampere gets converted to more useful milliampere level. High voltages ranging from 500 volt to 5000 volt are required for normal functioning of the device. When cathode is not illuminated, flow of dark current is observed, which is due to thermal emission and use of high voltage electrodes. It should be noted that number of electrons emitted is directly proportional to the wavelength of the incident illumination. The advantages of photomultiplier tubes are: first, they have high frequency response. Second, they have high sensitivity, that is as high as 20 angstrom. 20 amperes per lumen when compared with 100 for a photoelectric cell. Third, depending upon the cathode material, the spectral response can vary from 100 nanometer to 1000 nanometer. The drawbacks of such tubes are their bulky design, high cost, and require high voltage for their operation. Because of their incredible amplifying capabilities, they are used extensively in photoelectric measurement, control devices, and scintillation counters. Students, now let us consider the photoconductive cells. Certain semiconductors are sensitive to incident light striking on their surface. This striking of light provides sufficient energy to electrons within the material and they break away from their atoms, leaving behind positive charge carriers known as holes. This sudden increase of charged species within material increases the current flow at an applied voltage. At a fixed applied voltage, flow of current increases with increase in light intensity incident on its surface. This effect can also be seen as decrease in resistance with increasing light intensity. It is due to this effect such semiconductors are called photoconductive cells or photoresistors and sometimes also light dependent resistors, that is LDRs. Commercially important photoconductive materials are cadmium sulfide, germanium and silicon. The spectral response of cadmium sulfide is quite similar to that of a human eye. They are often used where human vision becomes a limiting factor, such as street light control or automatic iris control for the cameras. The main components that make a photoconductive cell are ceramic substrate, a layer of photoconductive material, a moisture resistance enclosure, and metallic electrodes to connect to the circuit. The circuit symbol and construction of a photoconductive cell is shown in figure 4. The light sensitive material is organized in the form of a long strip, and this material zigzags across a disc-shaped base having protective cover or glass or plastic. The ends of the strip are connected to pins below the base. The illumination characteristics of the device are shown in the figure 5. From the graph, one can deduce that resistance is highest when device is not illuminated. This resistance is also known as dark resistance. On illumination, resistance falls down to few hundred ohms. One should note that scales are logarithmic to cover wide range of resistance and illumination possible. The sensitivity of the device is given in terms of cell current at a fixed voltage and given level of illumination. The major drawback of photoconductive cell is that it is quite sensitive to temperature variation and therefore unsuitable for analog applications. They have wide use in industrial and laboratory control applications. Now students, let us study about the photovoltaic cells. Photovoltaic cells are semiconducting junction devices and are used for converting radiation energy into electrical energy. They generate a voltage proportional to electromagnetic radiation intensity and are called photovoltaic cells. due to their voltage generating capability. These devices are active transducer and do not require an external power source. A silicon solar cell is one such example that converts radiant energy of the sun into electrical energy. A solar cell is thin slice of single piece of p-type silicon crystal. It is 2 cm square wafer and into this 0.5 micron thin layer of n-type material is diffused. The circuit symbol for a photovoltaic cell is shown in figure 6. The open circuit output voltage characteristic of a photovoltaic cell is shown in figure 7. The graph is logarithmic on light intensity axis. From the graph, one can deduce that the cell is more sensitive towards low light levels. A small change in light intensity, say from 10 to 100 lux, can produce the same increase in output voltage as a large change in light intensity, say from 100 to 1000 lux at higher light intensity level. Figure 7 shows the open circuit output voltage characteristics of typical photovoltaic cell. The photovoltaic cells can operate over wide range of temperature, that is from -100 to 125 degrees Celsius. An advantage of these devices includes their ability to generate voltage without any external bias and have extremely fast response, that is, they can convert energy instantaneously. Multiple units of silicon-based devices are used for light sensing applications such as reading punch card in the data processing industry. Students, let us now study about the photojunctions. There are two kinds of photojunctions, photodiodes and phototransistors. Silicon used in such light sensing semiconductors have spectral response peak near wavelength of 0.8 micron. For optimum response in infrared region, the germanium devices are preferred. These devices are sealed in special metal can with a window or lens fitted over it. This is to focus incident light onto the PN junction. First of all, let us study the photodiodes. They are two-terminal semiconducting PN junction devices and are designed to operate with reverse bias. The construction, symbols and biasing arrangement is given in figure 7. They are mounted on a translucent case or its semiconducting junction is mounted beneath an optical lens. The output voltage is collected across a series connected load resistor R. This resistor may be connected between the diode and the ground or between the positive terminal of the supply and the diode. This is illustrated in figure 7. In a reverse biased PN junction, a reverse saturation current flows because of thermally generated holes and electrons that are swept across the junction as the minority charge carriers. As temperature increases, more and more electron hole pairs are generated and this further increases reverse saturation current. Similar effect can be achieved by illuminating the junction. When the light strikes the p-n junction, it dislodges valence electrons, and with more light bombarding the junction, larger reverse current is generated by the diode. From the graph in figure 8, one can observe that the reverse saturation current increases linearly with increase in luminous flux. Now students, let us study the phototransistors. A phototransistor is like an ordinary bipolar junction transistor, with an exception of having a base terminal. The base terminal in a phototransistor is in the form of light. Thus, the current induced by photoelectric effects is the base current of the transistor. The standard symbol of the phototransistor is shown in figure 9. The device is usually packed in a metal case and have a lens on the top to focus light at the base terminal. The photogenerated currents of the base collector junction are directly fed into the base of the device. This produces a nominal current amplifying transistor action, resulting in the output current. In practice, both emitter and collector current are identical. Since here base is open, the device is not subjected to negative feedback. The curve for the base current versus illumination level is shown in figure 9b. The main difference between a photodiode and a phototransistor is current gain. The same of light striking both devices produces more current in phototransistor than a photodiode. This difference makes a phototransistor more sensitive as compared to photodiode. Output currents in photodiode is in microamperes and can switch on or off in nanoseconds, whereas phototransistor has output in milliamperes and switches on or off in microseconds. So students, let us now summarize what we have learned in this module. In this module, we studied about various types of optoelectronic devices. These devices are also known as photoelectric transducers. Here, we have covered the following topics: photoemissive cells, which are of three types: photocell, gas-filled photocell, and photomultiplier tubes. We also studied about the photovoltaic cells and photojunctions, which are of two types, that is the photodiode and phototransistor. Thank you.